Okay, let's go through this practice test. Maybe we'll go through two of them. I don't know. We'll see how long this takes. A vector does require both magnitude and direction. That is true. Which of these is a scalar quantity? Speed. Slope of a position versus time graph represents velocity. There are better ways to say that. I would say the derivative of position is velocity, and the slope of the tangent line at a particular point is the velocity at that point, but that's what they meant. It's true. And Newton, remember F equals ma, right? Mass times acceleration. So what's mass measured in? Kilograms. Acceleration, meters per second. Excuse me, meters per second squared. So kilograms times meters per second squared. You throw a projectile. Projectile means the only force is gravity, and that's pointing toward the center of the earth. So there's no air resistance. I mean, we can have projectiles with air resistance, but we usually, I don't want to say we won't call them projectiles because they're still projectiles, but I'm rambling now. So our only force here is gravity, no air resistance. The horizontal component of velocity remains constant. That is true. There's no such thing as centrifugal forces. They don't exist. They're what are called fictitious forces. So if we got a car going around a curve, we've got its weight pushing it down, its normal force pushing it up. Neither one of those is going to point toward the center of the circle. The only thing that does is friction. Now, the force of friction is proportional to the normal force in magnitude, but that's just to find the magnitude of the friction. It's the friction that points toward the center. This is false. Oh, no, I read it backwards. I lied to you. If the net force is zero, the velocity is constant, not necessarily zero, constant. That is true. That's the first law. Okay, so you're moving, you're on a bus, the bus comes to a sudden stop. Why do you keep moving forward? Because you have inertia, because no outside force has acted on you until you hit the seat in front of you. That is the first law. Static friction always acts opposite of the to the tendency of motion. That's worded really weirdly. I'm gonna have to check and see what Chat GPT. I would never ask a question like that. Friction op points in the opposite direction of slipping. In whichever direction slipping would occur, that's the direction opposite from which way static friction points. So if I'm walking across the floor and I'm moving to the right, my motion is to the right, but my feet are trying to move to the left, but they won't slip because of static friction. That static friction opposes my foot pushing to the left, so it points to the right. That's what makes me go to the right. So you got to be careful when you're thinking about this. When I say tendency of motion, it's a weird way to phrase it. We're talking about the thing that's actually grinding against the other surface, not the whole body itself. It is true. I just would not have worded it that way. You're pulling a block across a horizontal surface at constant speed. Do we have friction? We must have friction here. I really don't like the way they worded this one. None of these are true. What they mean, again, I'm going to have to check the solutions, how it answered this question. The magnitude of my applied force is going to be equal to the magnitude of the frictional force. The weight and the normal are both vertical forces. Those will be equal and opposite. But this is a force. That's a vector. That points in a certain direction. This will point in the opposite direction. Those are not equal as vectors. They're equal and opposite as vectors. That's not a third law pair because they're acting on the same object. This is what I think they meant, but they should have said here, the magnitude of the applied force equals the magnitude of the frictional force. If they had said the net force, the answer would be 0. Because we're moving at constant velocity, so all the forces add up to 0. Normal forces do always point perpendicular to the surface. Net force always points in the same direction as acceleration, F equals ma. An object moving in a circle. That means your velocity is changing. Velocity is magnitude and direction. If your direction's changing, your velocity is changing. If your velocity is changing, you have to have some non-zero acceleration. That is false. In fact, if you're moving in a circle at constant speed, you'll have acceleration, centripetal acceleration. It'll point toward the center of the circle. Let me make sure I am recording all this. Okay. F equals ma. If the net force doubles, the acceleration will double. Yeah, that's what weight means. Which of these is not a contact force? Gravity is the only non-contact force we deal with this semester. That is true. That is Newton's second law. This is Newton's third law. That's what equilibrium means. And we've talked about this is not really the best way to define inertia, but it doesn't say the measure. It's a measure of an object's inertia. Okay, some short problems. I don't know that I have enough space to do all these on here, but I'm going to try. So I may have to zoom in and write really small. All right, so we're pushing on a horizontal floor here. That is meant to be horizontal. Mass equals 2 kilograms. Say I'm pushing this way. Here's my applied force. If I draw my free body diagram, my weight's going to go down. My normal force up. Here's my applied force. Maybe I'll call it FA for applied. And then my frictional force is going to oppose slipping, and it will be a kinetic frictional force. That'll point in the opposite direction. This guy is going to win. So our net force is going to be to the right. Okay, some of the forces in the y direction must be 0 because we know we're not accelerating up and down. So that implies the normal force plus the weight vector as vectors add up to 0, which means the magnitude of the normal force equals mg. Because this was mn minus mg equals 0, so magnitude equals mg. And remember, like this is pretty common. If I were to just write this, I mean the magnitude of the normal force because I didn't put a little vector on it. We're going to need that because we know our frictional force in magnitude is mu k times the magnitude of n. So that would be 0.25 times 2 times 9.8. And I'll get the calculator out in a minute and figure that out. Okay, Sum of the forces in the x direction. We'll be adding as vectors FA plus FK. And I know this is a negative because I can see that in my picture. All right, so that will be 10 minus, yeah, I'm going to need the calculator. I have my calculator closed. Hold on, let me pause and get that out. All right, so we got 0.25 times 2. Where'd I get 2 from? Is that my mass? Let me double check that. Yeah. All right, 4.9. So 10 minus 4.9 will be 5.1. That's my net force. F equals ma. Sum of the forces as vectors will be the mass times the acceleration vector. So this guy here, this implies AY equals 0, or really the other way around. We know AY is 0, so that's how we got this. This one implies the sum of the forces in the x direction is the mass times AX. So 5.10, 5.1 will be 2AX. So AX will be 5.1 divided by 2. What is that? 2.55 meters per second squared. Okay. Ball's thrown straight up. So we're going to draw out axis here. So we're going straight up, straight back down. In fact, we could look at this. Sometimes it's better, instead of graphing X versus Y, maybe we'll just look at T versus Y. So here's some time, maybe time 2, some time 1, time 0. Y0 is 0. I decided that. We don't know Y1. We do know V0 is 15 meters per second. It's a one-dimensional problem. There are no x's to worry about. We're throwing it straight up and straight down. Okay, we know V1 at the top there will be 0. So we have our 3 equations. It's 1/2 AT squared. V equals V naught plus AT. I don't have to put subscripts on everybody here because we only have y's. And V squared equals V naught squared plus 2a delta y. I know both of these. I think the easiest way to do this, and we could use these 2 equations, but I'm going to use these 2, use this to solve for the time, and then plug that up in here. Okay, so using this equation, we'll have 0 equals 15 minus 9.8 t. So t is 15 divided by 9.8. It's a little over 1. 1.53, sure. Always go at least 2 places. And then y at that time will be 0 plus 15 times 153 minus 4.9, half of a. Remember, a is negative g. G is always a positive number. We decided right here that up is the positive direction, so a is negative. And half of g would be 4.9. 1.53 squared. All right. So 15. By the way, you can do this. You can do times second answer minus 4.9 times second answer squared, 11.5-ish. So we'll call it 1148. Don't forget units. Meters. Okay, next problem. It's a centripetal motion problem. All right, so we're going to look at the back of the car. So I'm always bad at drawing cars. That's the back of the car. That says back. That does not say back. All right, so we're going to have the weight pushing down, the normal force pushing up, and we'll have some frictional force here, some static frictional force pointing toward the center of the circle. So we're looking at the back of the car, and it's trying to turn to the left. Or sorry, to the right. And that way is right. So the car is trying to turn around like this, trying to go that way. The tires want to slip out this way. See, he's out here on a curve. He's right here. The tires want to slip that way, so some frictional force will point back toward the center of the circle, C. So if we draw a free body diagram, weights down, normal forces up, and Fs points toward the center of the circle. And just put a big capital C here to indicate the direction of the center of the circle. Then some of the forces in the y direction must be 0 because we're not accelerating up and down. And just like always, that will imply, not always, but whenever we have cases like this, these two must be equal and opposite. So the normal force must equal mg. We know Fs in magnitude equals mu times the magnitude of n. Oh, we're just looking for the frictional force. Okay. So we're not reaching the point. This one's worded kind of weird. We're not reaching the point of slipping. So this is a static frictional force. So this one's a little tricky. The frictional force in magnitude is less than or equal to mu n. If we hit this point, if we hit mu times mg, we're going to start to slip. We haven't gone that fast yet. So we're going to figure out the actual magnitude, and it's going to be less than this number. Otherwise, we would have started slipping, required to keep us on this circle. So our centripetal force is the net force. Anytime you're moving in a circle at constant speed, and that will always point toward the center of the circle, and it's whatever's left over that didn't cancel. That is our frictional force. And in magnitude, anytime you're doing centripetal motion, mv squared over r. That's just mass times centripetal acceleration. And remember, centripetal acceleration is v squared over r. All right, so this is what we're looking for. Fs will be m v squared over r. So 1200 times 14 squared divided by 50. 4704 newtons. At that speed, that's how much friction we actually feel. If we were going faster, if this number got bigger and ended up getting bigger than this, we would start to slip. So the question didn't ask for it, but we would slip when that frictional force gets bigger than mg, which would be 1200 times 9.8, which is like 12,000-ish. Like we'll get an exact number here if you want it. 11,760. Again, this question didn't ask for it. But if our friction got bigger than this, that's when we would slip at the moment it reached that. So we'd have to be going faster. We could figure out what speed would we need to be going to make this number equal that by just setting this equal to that and solving for V. Remember, there are a lot of different ways we can ask these questions, but this was the answer to the question they asked. Okay, velocity is just the, right here. Just the derivative of position. And we take the derivative component-wise. So I'm going to write it in vector form instead of ij form. Same thing. Like maybe for fun, we'll write it both ways. So I could have written that 6t I hat, that's an I hat, plus 4 j hat. And acceleration is the second derivative of the position vector, or the first derivative of acceleration, and that would be 6, 0. Just take the derivative with respect to time here. And if we wanted to write it in ij notation, that would just be 6i. You actually wouldn't have to write the plus 0j, but you could. Okay, these are good questions. I like these a lot. Hint, hint, hint. Wonder if anybody's actually watching this. I hope I'm recording. Okay. Displacement is change in position. So part A. So I want x of 6 minus x of 0. It almost got me. It almost got me. This is not a graph of position versus time. This is a graph of velocity versus time. Displacement over some time interval is the antiderivative from A to B, that your two different times, of v of t dt. So I want this area. So the antiderivative from 0 to 6 of v of t dt, it looks like it's probably going to be 0 because all this positive area will probably cancel out this negative area. Let's see, we got 3 times 2 times a half, that's 3. That's what this guy's area is. 1, 2, 3 times 2 times a half, area of a triangle, but that guy's negative, minus 3 equals 0 meters. Distance is not the absolute value of what we just did. This is a very common mistake. You don't just take that answer and take its absolute value. No, distance is the antiderivative from A to B of the absolute value of your velocity function. So you have to redraw the velocity graph and make it all positive instead of having any negatives. So that's 3, that's 6. Here's 2 where that peak happens. There's 4. So I just took this chunk, and flipped it over, made it positive. These have both have areas of 3. So 3 plus 3. My distance traveled is 6 meters. Okay, now some longer problems. I'm going to try to squeeze these in here. Let's see if we have. Okay, so we're on an incline. I got a box. 25-degree angle. We know weight's going to push down. We know normal force is going to point perpendicular to the surface. The box wants to slide down the hill here. So friction's going to oppose slipping. And I'm just going to put little cap or lowercase f because I'm not sure if it's big enough to overcome the static friction or not. If it's big enough, then this is the frictional force we'll end up using. That's our coefficient we'll use. Okay, we're going to rotate our reference frame. Normal force will point straight up because this is now my x-axis, and here's my y-axis. My frictional force points to the left, and my weight will point at some angle, and we've seen before we end up getting a 25-degree angle right here. And we could do that. Let me draw this out a little better. So this was a right angle. My weight was pointing down here. This was a 25-degree angle. This angle in here is 90 degrees. Let me pause. I always have to think this one through. Okay, yeah, so here's my incline. I'm just redrawing this picture here. Here's the incline. Here's the normal force here. Here's the weight straight down. So again, I'm redrawing this picture. The normal force is perpendicular to the surface. If I draw in this, here's the ground. The ground and the weight vector are perpendicular. That means that these two, this is my new y-axis here, this is my new x-axis. These guys here are perpendicular, right there and there, the x and y-axis. So if this is 25, this guy in here is 90 minus 25, which would be what, 65? But these two are perpendicular. So these two angles here have to also add up to 90, making this guy 25 again. So yeah, that angle right there is 25. You always have to use geometry to find that angle from the W vector, and I can never remember whether it ends up being this one or that one. I guess you could just memorize it. Okay, we have to break that weight vector up into components. So here's a 25-degree angle. Here's WX, here's WY. Remember your WX, your WY, your components of your vectors, always put them on the outside. Here's your magnitude. Magnitude is the hypotenuse and it's always positive. All right, then we can see WX will be negative. I can see it from the picture. Magnitude of W, which is just mg, sine of 25 degrees because that's opposite the angle there. WY is also negative magnitude, but now cosine 25 degrees. And we can go ahead and figure out what those are. So M, we know G, sine, cosine 25. I literally just had it, 5 kilograms. So 5 times 9.8 times sine of 25. 20.71. Excuse me, and he's negative. That looked ugly. And then, like, if you're really careful, you can just do this on your calculator. Scroll back up, grab that guy, come back here and change that to a cosine. You just got to be really careful. Make sure everything's where it's supposed to be. 44.41. And remember, he's negative. Okay. My normal vector points up, friction points over here. Sum of the forces in the y direction, remember that my y direction points along the normal vector, must equal 0. So that implies the normal vector plus wy, which is a negative, must equal 0. So the normal vector is the opposite of that. Or we can just say, like here, magnitude of normal vector minus 20.71 equals 0. So the normal vector is 20.71 newtons. And yes, it's weird that I've got Newton and normal. You just got to know from context what that means. Why do I need that? Because I need the frictional force. So friction, if it's static friction, will always be less than or equal to mu times the normal force. Okay, what about in the y direction? Or sorry, in the x direction. Some of the forces in the x direction. So I've got this Wx here, the Wy here, and the normal force. We already dealt with those. Those cancel out. Wx and friction. And you may be saying, Professor, why did you draw your triangle over here instead of over here? It doesn't matter. Like, yeah, sure, it would have different angles in it, but I still would have gotten the same values. If you want to look like that other picture, sure, here's Wx, here's Wy. These two canceled out. These two are not going to cancel out because we're probably going to slide down the incline. So we've got the frictional force. Oh, that's a capital F there. Frictional force plus Wx. And that's going to end up being mass times acceleration in the x direction. Okay, how big is Wx? 20. Wait, something's not right here. Oh, I hope somebody caught this. Right here. Let me get my eraser. I copied the wrong number right here. Okay. Like I wrote Wy, but then I copied down the Wx number. Minus 4441. Okay. So this is going to be bigger than that could possibly be. So what is my biggest possible frictional force? So Fs max is when these are equal. And that'll be 0.40 times 44, 0.41. Now it's right there on the screen, so times 0.4. 17.76, I think it was, newtons. But my Wx is bigger than that in magnitude. So we moved past static friction and we're into kinetic friction. So yes, it moves. We just had to check and make sure that this maximum value for static friction was less than the actual applied force coming from the weight pointing in the x direction. This is going to overpower the maximum possible static frictional force. So now we're in the realm of kinetic friction. So the sum of the actual forces we'll feel in the x direction is kinetic friction plus Wx. Kinetic friction, I'm kind of running out of space here, just always equals mu k times n. So that would be 0.30. It's smaller than that value times 44.41. That was my normal force. To 44.41 times 0.3. Is that what it was? Yeah. 1332. All right, so what do we get here? We get 13.32 minus 20.71. So just here, minus 20.71. My force down the hill will be negative 7 point, let's call that 39. Okay, what they asked for though, the acceleration, F equals ma, right there. So that negative 7.39 must equal the mass times the acceleration in the x direction. Remember, x direction is right here. Y direction was perpendicular to the surface. X direction is along that incline. So A will be that divided by the mass. What was my mass? 5. So just divided by 5. Negative, because we're going downhill, 1.48 meters per second squared. Okay. All right, we got a projectile launching off a cliff. We want to know how long does it take to reach the ground and what is the horizontal distance traveled. So draw a little cliff here. This is 30 meters. I can choose wherever I want. I'm going to choose right here to be x equals 0. I could have chosen that anywhere. Here's some x1. Y0 will be up here on top of the cliff. And then we're going to go over here. T0 equals 0. We're projecting it. I should draw my picture to illustrate that. We're not throwing it up in the air. We're just going to toss it horizontally off. Still going to fall on a parabola, but it's not, there's no arc. All right, T0 equals 0. I do not know T1. V0 is all going to be in the x direction. Is 18. V0 in the y direction will be 0 because our initial velocity, here's my initial velocity vector, at times 0, it's just a horizontal vector. Okay, so this is a pretty easy version of the problem. Let's write down all of our equations. X equals x naught plus v naught xt. Vx, this one isn't really an equation, it's a statement that your x velocities don't change. Y equals y naught plus v naught t plus 1/2 ay, of course, t squared. V equals v naught plus at, and that's in the y direction. And these are all y's. Vy squared equals v naught in the y direction squared plus 2a, again, ay, but it's our only a in the problem, delta y. Okay, I want to know when does y equal 0? We know this. We know over here at y1, our height is 0. So I could use this and find my final velocity because I know this, I know this, I know a. And then I could come back up here. Well, no, I wouldn't be able to do anything with that because I already know all this stuff up here. Oh, no, I could. Sorry. I could use this equation, find the final velocity, plug that in here and solve for time. Or I could just use this top equation and solve for time. So y1 should be y0 plus v naught in the y direction, t1, remember these have to go together, plus 1/2 a t1 squared. I know both y's. I know v naught. I know a. A, of course, is negative g. So I can solve for t1. So 0 equals 30. It's really easy to get these backwards and these jumping off a cliff kind of problems. It's really easy to put 30 here and 0 here, and then that messes everything up. Like you'll get imaginary numbers. Let me make sure I'm recording because I know I hit pause earlier. Okay. V naught was 0, so plus 0, minus 4.9, half of g, negative half of g, t1 squared. All right, so I'm going to move the 30 over, divide by negative 4.9. I'll get t1 is the square root of 30 over 4.9. I should have done the square root there. Square root, second answer. 247. And that's in seconds. Listen to me. Trust the equations. I remember when I was taking this class, I would try to work this out logically. I'd be like, well, the acceleration is negative 9.8. So after every second, you're going to lose 9.8 meters and blah, blah. No, that's not the way it works, first off. That's the acceleration, not change in position. That's not a velocity. Velocity decreases by 9.8 every second, not position. So you might look at this and go, oh, it's 30 meters. Just divide that by 9.8 and that'll tell you how many seconds it'll take. No, it's not distance equals rate times time here. This is an acceleration, not a velocity. You're not going to logic your way into a numerical answer. Trust the equations. Okay, how far from the base does it land? Now, my interpretation of that is here. Well, yeah, from the base. Like we don't have to find this distance here. Yeah, they definitely mean find x1. So we would just plug t1 up in here. x1 would be x naught plus v naught in the x direction times t1. Well, that's 0. What was v naught? 18. This one is distance equals rate times time. In the x direction, we're going at constant velocity. Distance equals rate times time. And if we want an exact answer, I've already got that approximation there on the screen. Just take that times 18. That's better than using the rounded version. And it's less typing. 4454. Okay, how many more of these we got? I hope I can get through this. I got class in a few minutes. Okay, we got a passenger standing on an elevator that's accelerating downward. Phone's doing stuff. Okay, you got to think about this for a little bit. We're talking about you. You're standing in the elevator. Your gravity's pulling you down. Let's say the elevator is not moving. Why are you standing still? Because the elevator is pushing back up on you, right? That's your normal force. When the elevator's not moving, these will be equal and opposite. If the elevator is accelerating downward, you're going to feel less of a normal force. You're going to feel like you weigh less than normal. That's why you feel kind of weightless. Well, you get that little flurry in your stomach when the elevator is going down. The normal force is going to be less than the weight. You are accelerating at the same speed or same acceleration as the elevator. So forget about the elevator. You have an acceleration of negative 1.5 meters per second squared. The sum of the forces on you, this is you we're talking about here, must equal your mass times your acceleration. So that means your weight as a vector plus your normal force as a vector must equal your mass times your acceleration vector. All right, so what we got here? Negative mg plus your normal force must equal 70 times negative 1.5. That looks ugly. Let me fix that. Okay, we know M, we know G. So let's fill those in. What is that? Negative 70 times 9.8 plus N must equal whatever that is. So let's do both of those calculations. 70 times 1.5. So negative 105. And what was this? 70 times 9.8. It's going to be around 700. $686. So negative 686 plus the normal force is negative 105. So the normal force will be negative 105 plus 686. That's a 686 there. So 686 minus 105. 581. This is what you actually weigh. If you get on a scale and you're standing still, nobody's accelerating, your weight is 686 newtons. If you're in an elevator that's accelerating down, that scale is going to read less. Scales don't read your weight. Scales read the normal force. So that scale would show that you weigh less because your net acceleration is down. If you were free falling, the scale would read 0 because you wouldn't be pushing on the scale. Scales don't read your weight, they read the normal force that they're applying to you. That's called your apparent weight. So for this elevator, because it's accelerating down, your apparent weight is less than your actual weight. If we were accelerating up, if we had a positive number here, this would be more. If you're in an elevator that's accelerating up, you feel like you weigh more than normal. That's called your apparent weight. If you're accelerating downward, you feel like you weigh less than normal. And when we say accelerating, we're not even talking which way we're moving. So think about this for a minute. You could be in an elevator that's going up, but slowing down. So think about this. This is a really good conceptual question. You get in an elevator, it's moving up. You're going from the first floor to the 10th floor. You've almost reached the top and it starts slowing down. You're moving up, If you're slowing down, that means your acceleration must be opposite your velocity. So velocity is up, acceleration is down. Because you're slowing, these have to be in the opposite direction. You would weigh less than normal. If you're in an elevator that's moving upwards but slowing down, a scale would read less than normal. Okay, what if you're moving up? So velocity is up and you're speeding up. So the elevator has just taken off. You get in the elevator and it just starts taking, you're going zero now, and all of a sudden it's moving at 3 meters per second, whatever. You had to accelerate upwards. So your acceleration is in the upwards direction. Both of these are in the same direction because you're speeding up. If you're speeding up, velocity and acceleration point in the same direction. Then you would have had a positive acceleration and you would have felt like you weighed more than normal. Like, you know this, when you get in an elevator and it starts moving up, you feel a little bit heavier because you are. Your mass hasn't changed, but your apparent weight has changed. And everything's the opposite when you're going down. Okay. Well, I got a few minutes. Atwood's machine. I'm not going to put Atwood's machine on the test. We're going to do this problem. So you got M1. You did this as a group assignment. Here's M2. We've got a tension here. We've got a tension here. We know we have the same tension. Draw a free body diagram for both. I'm not going to go through the whole thing. Weight 1, T1, weight 2, T2. We know that both of these have to have the same acceleration in magnitude. We know both of these tensions must be the same. So magnitude of T1 equals magnitude of T2 equals T in magnitude. This guy's gonna, whoever's bigger, let's see. This guy is 3 kilograms. He's 5 kilograms. He's going to win. He's going to accelerate down. He's going to accelerate up. His acceleration is negative. His acceleration is positive, but they're tied together, so they have to have the same magnitude. All right, so for block 1, sum of the forces in the y direction will be T, that tension up, minus his weight, mg1, and that must equal m1 g1, m1 a1, call that 2. For m2, sum of the forces in the y direction, T minus m2 g2 must equal m2 a2, but we know, let's see, this guy is a positive acceleration, he's a negative acceleration. So that'll be positive A, that'll be negative A. So from the first equation, we get T minus M1 G1 equals M1A. And from the second equation, T minus M2 G2 equals negative M2A. Because he's got a negative acceleration, he's got a positive acceleration, but they have the same magnitude. And then we just solve for T, solve for A. We solve the system. There's some complicated algebra that happens here. I don't like putting this problem on an exam. ChatGPT just picked this. Okay, we just did an inclined plane problem. I want to make sure I have time to get through all of these. All right, we got our box here. We draw it like this. We got our box here. We know the way it's going to push down. We're applying some force, some F applied up the hill. We know the normal force points up this way, and we know friction is going to stop me. I'm trying to push it up. Friction's going to point in the opposite direction. It's trying to slide the opposite direction of slipping. We rotate our reference frame so that the normal force is pointing up the y-axis. So this will be the y-axis here, right there, and this will be the x-axis. So that applied force that says FA there. Here's my frictional force. It is going to be kinetic friction. And then my weight will point down at some angle. And we just saw from that last example that that will be the 20-degree angle right in here. Okay, we got to break that weight vector up into components. Here's magnitude, which is mg. This is wx, this is wy. And this is 20 degrees in here. Okay, then wx will be negative mg sine of 20 degrees. Wy will be negative. They're both negative. We see that from the picture. Look at this. I'm pointing backwards and I'm pointing down. Cosine of 20 degrees. All right, what was mg? 10. All right, so 10 times 9.8 times, oh, we'll do sine first. Sine 20. Negative 3352. And then if I'm really careful, I can just go up, grab that guy. I hit enter to grab it on this calculator. Replace that sine with cosine. 9209. Negative 92.09. And they're both negative. Okay. So here, sometimes it helps to put everything in one picture. This was Wx here. This was Wy. In the y direction, some of the forces in the y direction will be the normal force plus Wy, keeping in mind that that's a negative number. That must equal 0 because Ay is 0. I'm not accelerating up perpendicular to the plane here. So that tells me my normal force will be 92.09 newtons. Because that minus that, move it over. Okay, sum of the forces in the x direction. I've got my applied force plus my frictional force I'm going to have to find in a second, plus Wx. And he's a negative number also. He's going to end up being a negative. We know that from the picture. All right, how do we find the magnitude of Fk? That's mu k times the magnitude of the normal force. So 0.25 times that thing we just found. How did I know to do things in this order? One, experience. Secondly, order wouldn't have mattered here. I could have written all this out first and realized, oh, wait a minute, I'm going to need that normal force. Let me write out the other equation. You're always going to have this equation and this equation. Some of the forces in the y, some of the forces in the x. What am I doing? 0.25 times 92. I didn't need parentheses, but it's what I accidentally typed and it'll work. Oh, I'd already done that. All right, I just needed to write it down. Sorry. 23.02. That's just magnitude that we just found. I'd look at the picture and see that that's negative. Okay, so this will equal mass times acceleration in the x direction. So now let's put everything in. So I'm coming back here. FA was 120 minus 23.02 minus my x component of my weight, and that will equal the mass times A. So I've got 120 minus that last answer, minus 33.52. Get that in my calculator first and then divide by 10 to get A. 6 point, let's call it 35. Meters per second squared. And that's going to be up the hill because this is a bigger force than that and the weight combined. I mean, you can see there. Okay, now we're drawing some free body diagrams. I think I'm going to be able to finish all this. This one's easy. Weight's down, normal forces up, no forces in the horizontal direction. All right, so we're assuming here, I'm assuming the car is accelerating that way. Weight's down, normal forces up, the acceleration. So we have some applied force here from the friction that comes from friction. The tires gripping the road that points in the direction we're accelerating. Okay, now this is a rough floor. So we got the block, the weight of the block, the floor pushing back up on the block. I'm pulling it. I'm assuming here that I'm pulling it to the right. They didn't tell me, but I'm going to assume I'm pulling it to the right, and then friction is going to fight me. This will be some kinetic friction pointing in the opposite direction. I'm sliding it that way. Friction is going to try to pull it back to the left. I'm going to win. Okay. If we're accelerating upwards, the sum of the forces in the y direction must be mass times AY. I'm accelerating up, so AY points up. That means the net force must be up. That means the vector pointing up here must be bigger than the one pointing down, because this one has to win to give me something left over here to make me accelerate up. If I were accelerating down, this one would have been bigger. Again, this does not even mean we're moving upward. If we were moving down, if velocity was down, but I was slowing down, when you're slowing, velocity and acceleration point in the opposite direction, acceleration would still point up. Moving down, but slowing down still has a positive acceleration in the upwards direction. And remember, if you stand on a scale, the scale reads your normal force. That's bigger than the weight here. I would weigh, according to the scale, more than my actual weight in this case. Or we might be moving up and speeding up. If we're moving up and we're speeding up, if you're speeding up, acceleration and velocity point in the same direction. We'd still get acceleration up. That was our given, that was acceleration was up. And I believe that is it. Real quickly, let's take a look at all the answers that ChatGPT spit out. And let's compare. Wonder if I can get these side by side. I got to get to class here in a minute. Hey, true. D, true. B, true. B, true. I'm just seeing how good of a job it did. A, true. C, true. What am I on? 12B, false. Double, true, gravity. True, true. B, true, true. Oh, there's an extra question here. I don't know why there were 21 here and 20 here, but all the ones I went through I got right. Or they got right, I think. All right, we got 2.55, 1148. Yeah, they wrote it in scientific notation. Yep, those are right. I already looked at these. Acceleration, negative, down the plane. I like how they wrote down the plane. This free body diagram isn't the best. Like that's not really very good. I don't know what's going on here with this frictional force. That frictional force should have been pointing up the plane. So that's one that got by me that I didn't catch. 44, 2.47, 581 newtons. So this is what you get for acceleration. And then once you plug that back into any of these equations to solve for tension, like you could work this one on your own if you want. Yep. And then did it get the free body diagrams right? Yeah, I don't know which one I'm on. Okay, I guess I'm there. Sorry, trying to get that out of my way. I wish it had drawn this normal vector bigger. That's what I would be looking for here. If I asked you to do this, you definitely want to draw this to scale to speak. Make sure that normal vector is obviously bigger than the weight vector. I wish it had done that there. Overall, though, I think ChatGPT did a decent job. Okay, I will post this video. I don't think you need to hear me say that, but I'm going to post this video. I guess I can just stop talking now. I guess I'm going to keep recording while I export this PDF. Did I call it my solutions? My solutions. Yeah, the video is over. Like you can stop at any time now. All right, now I'm going to stop.